Good morning. We are Group 7 and this is our Team Reactor Simulation Project.
This chart shows the data recorded from our simulations of manipulating the position of the control rods in an AP1000 reactor. We began with the rods at 98%, decreased their position to 85%, and then increased their position back to 95%. Several steady state values are also recorded. This graph shows the position of the control rods versus the time that the simulation was run. The flat lines on the graph represent the time spent at a steady state value. This graph shows the core thermal power of the reactor versus time. The core thermal power is directly proportional to the rod position. This is because as the rod position decreases, there's more of the rods available to absorb neutrons and therefore less power is produced. The opposite is true as the rod position is increased. Less of the rods are available, so less neutrons are absorbed and more power is produced. This graph shows the steam generator pressure versus time. The pressure in the steam generator always increases due to steam buildup inside the reactor. Tatum will discuss the steam generator in more detail later. This graph shows the turbine demand versus time, which is directly proportional to the rod position. If there is less power produced by the reactor, there is less need for the turbine. When there is more power produced by the reactor, there is more need for the turbine. This graph shows the coolant temperature versus the pressure in the pressurizer of the reactor. The pressure generally fluctuated around a single value because the pressurizer is meant to keep the reactor at a constant pressure to prevent it from being damaged. The K value is related to the reactivity of the reactor by the equation seen below the graph. When K equals 1, the reactor is said to be at criticality. K is less than 1 with dramatic spikes at the steady state values when the rod position is decreased, and K fluctuates around a single value as the rod position is increased.
Exercise 2 was the plant load maneuvering with the turbine leading. Turbines work by having pressurized steam flow through the assembly to rotate the blades on the turbine. Each rotation of the turbine takes the energy and converts it into mechanical power. A reactor is brought to full power when the operating temperature and pressure is increased by means of rod position adjustments. With a decrease in turbine demand, the control rod position percentage is also decreased, as shown in the rod position versus time plot. When the rods are lowered into the reactor, the core thermal power decreases, as Alexa previously discussed. When the turbine demand slows, the pressure increases in the steam generator because the blades are not moving as quickly. This causes the pressure buildup, which is reflected in the plot. Turbines are a component of the secondary loop and are 90% or more efficient. At times of 250, 1200, and 2000 seconds shown on the graph shows a lag whether changes were being made to the turbine demand percentages.
When a reactor trips, the control rods are inserted directly into the core in order to shut it down. This process usually takes about 3 seconds to do, and the effects of this can be seen in our data collected in the graphs we constructed. This first graph represents the neutron flux plotted against time. We tripped the reactor at 160 seconds, which is shown by the immediate drop in flux. The control rods, when inserted into the core, hinders the neutron's ability to travel distances long enough to cause fission, resulting in the shutdown of the reactor, because without fission, a reactor is rendered ineffective. This graph is fuel temperature versus time. The jump in fuel temperature happens when we tripped the reactor at 160 seconds. There is a difference of about 1500 degrees Fahrenheit in the span of roughly 35 to 40 seconds. The reason there is such a drastic jump is due to the almost immediate halt of fissions in the core, which is what generates the heat. Without the heat, the temperature of the fuel will drop and then will continue to decrease very slowly. This slow activity is referred to as the decay heat, which could take weeks to decline entirely. This graph shows the typical behavior of decay heat once the reactor is shut off. Here we see a different trend. There is an increase in the pressure of the steam generator. The cause of this increase and then the constant pressure is because the decay heat from the core causes pressure buildup. In a reactor trip, the fissions may stop, but the fission products are still around and radioactive and will produce heat due to radioactive decay no matter what. In the event of an emergency trip, the integrity of the steam generator turbine system will try to be preserved.
The importance of simulation is crucial to see how each subsystem will behave when alterations are applied. Simulation is not always 100% correct, but is a good prediction of what could happen in real life.